Okay, so we are supposed to prove or disprove that the function from the reals to the reals where f of x equals x cubed plus 7 is bijective. So over here, this wouldn't be part of the proof, but just as a reminder what we're talking about here. So we're saying we have all the reals over here, all the reals over here. If we took any specific real and map it through this function, could there be another another element in the reals that would also map to the same number? If so, it's not one-to-one. So if we're showing one-to-one, we're showing if this situation happens, then x1 has to equal x2. The only way for 2 points to map to the same point is if they're the same point to start off with. And then the onto part, or the surjective part, is no matter what we choose in the real numbers here in our codomain, whatever we choose, there has to be an element over here that will map to that one. So everything here in the real, every real number has to have a number that in the reals that maps to it through this function. No leftovers here that aren't getting mapped to. Okay, so let's start off with one-to-one. We're going to use a little good proof language here. We start by showing that f is, I'm going to use the fancier word, injective. One-to-one could be the one-to-one correspondence, which is the same as bijective, or one-to-one, which is just injective. So because of that ambiguity, we use one-to-one all the time, and we usually mean injective. However, I'm just doing this for clarity. Either one is fine. So to do this, let's just choose two real numbers such that such that they map to the same point. So when we put the first point through this function f, whatever number it maps to, the second number x2 is also mapping to that same one. So again, the only way this should happen, if the function is injective, the only time this could happen is if x1 equals x2. So that's what we're going to be showing here. So we have this. So we say since we know this is true, it's part of our assumption. Well, let's just put x1 through the function and put x2 through the function. And we would just need to subtract 7 from both sides and then take the cubed root. And cubed root of a positive is a positive, cubed root of a negative is a negative. So this is just going to give us x1 equals x2. So we've shown that if this situation ever arises where two numbers are mapping to the same number, then they have to be the same number to start off with. So f is injective. And we go over here to prove f is surjective. Now I could just say onto here also. I'm just match the fact that I said injective, I'm saying surjective, but onto would be fine. To prove f is surjective, let's choose. Now we have to want to be clear that we're choosing a b from over here, that we're choosing some element in the codomain. Now the domain and the codomain are the same in this particular problem, but in general they're not always the same. So we're always picking a general arbitrary element here in the codomain. So let b be an r. We want to show that there exists some x in R such that f of x equals, and I was thinking about should I use a different variable there just for clarity, but I mean, I think we're okay here. Okay, so what do we do to show that? Well, we know what's going to get mapped to, so we might say something like, you know what, just, I want to do this, I think it might help clarify a little bit. So we want to show that there's some element in the reals. Now that x3 is going to be coming from here, from the domain, and when we put it through the function, it's got to equal this point here. So can we come up with that? Well, we know what f of x3 is. We can just plug x3 into our function. So we could say, don't know what I was doing with that capital I. Plugging x3 to f, we get x3 cubed plus 7 equals b. So all I did was took that equation and I substituted x3 in for the function. Solving for b, we have, or solving for x cubed, sorry, x3, we have x3 equals b minus 7, so that'd be taking the 7 over to the other side, subtracting 7 from both sides, and then taking the cubed root of each side. Now, we could, if I were going to write this in a textbook, I would have started off the surjective saying, consider x3 equals the cubed root of b minus 7. The only way I would get there is by going through these steps. This x3 will map to b. In other words, just for clarity, we'll take f of cubed root of b minus 7 equals, let's plug it in, cubed root of b minus 7 cubed plus 7 equals, well, the cubed root of a cube, or the cube of a cubed root is just b minus 7 . So f is surjective. F is surjective and injective, and it was given to us that it's a function. It is okay. There we go. So now it could be when you're going through, you might think, well, isn't any function then surjective? Well, no, that's not true. If this had been x squared plus 7, and we get to this and we have the square root, then you have to worry about positive and negative issues. Like you couldn't map to a certain negative number in that case. Over here, the injective, you would also have a problem with the x squared there. So not every function is going to work out like this. And you don't have to have a function like in algebra. Although, let me say this. So when you do have a function, to be honest, I have to think, it's not a real good drawing of this function, but my point is, being in a function is passing the vertical line test. In other words, no vertical line will ever cross the function more than once. That gives us that it's a function. Being injective is passing the horizontal line test. So that's why a function like this would not be injective, because you could draw a horizontal line and hit it into two spots. And then onto is just making sure that every y value is eventually touched by this function, and indeed it is. Although over here you can tell that these y value, whatever this y value is right here, is not reached. So again, that's x squared minus 5 or whatever this is not injective or surjective. So that's the visual interpretation of this.